Hi guys, welcome back. So in this video, let's study something called the maximum likelihood estimation. Okay. Now I'll tell you why we do this and what's its importance. So let's say that we have a data set, or let's say that this data set is a data set of data points that form a sample. It's not the entire population, it forms the sample. Now, if I have to draw inferences about the population, or if I want to find the population parameters using the sample, there are basically three ways you can do that. There are three techniques that help you do that. They help you draw inferences about the population from the sample. The first one is the maximum likelihood estimation. The second one is the Bayesian estimation. And the third one is the method of moments. Okay, so but the thing is, these out of these three techniques, maximum likelihood estimation is the most popular one of them all. So we will be concentrating on only maximum likelihood estimation. We won't do Bayesian estimation and the method of moments in this case. Okay. But yeah, this is maximum likelihood estimation is also used in industry and in academia to draw inferences about the population from a sample. So how okay, so whenever you start with the maximum likelihood estimation, let's say I have a data set of just 1 point over here, just 1 point for simplicity's sake. Now, what you do is the first thing that you do, I'll write the steps here. The first thing that you do is you start with a belief, okay? With a belief about the population, okay? This is important. So when I have this data set, I have this sample data point, and I start with the belief of that the population is normally distributed, okay? I start with the belief that my population is normally distributed. Population is normally distributed. So now I have to estimate the population parameters such as mean and standard deviation. So how do I do that? I basically, what I have to do is I have to take the probability that X belongs to the Gaussian distribution given some value of mu and some value of sigma, which is the standard deviation. All right. So one way of doing this is, I take a range of values for mu, let's say from 100 to 150, and then I take for sigma, which is again from anything 10 to 25. I take a range of values and I put it in the formula. The probability density function, sorry, the probability function for the for the Gaussian distribution is given by 1 by under root 2 pi sigma square exp minus half into exp minus half into x minus mu by sigma the whole square, right? This is the function for the Gaussian distribution. So now what I can do is I can just keep putting different values for mu and sigma. I have the range of values over here, and I can keep putting different values over here, and I'll get a range of probability values. Okay, and for whatever value of mu and sigma I get the highest probability value, I will choose that value of mu and sigma as my population parameter. Okay, so whatever samples fall on this data set, they will follow those population parameters. So now in this example, we we took only one data point. What if we have two? Okay, what if I have two data points like this over here? Let's call these data points x1 and x2. Okay, one data point is x1, the second one is x2. So again, what I have to do is I have to estimate the population parameters from this sample distribution. I start with the belief that this distribution or these samples, the population of the sample follows a Gaussian distribution. So I take p of x1 given mu comma sigma and I take whatever likelihood value I get from here. Look, I'll use the same technique that I used over here for this. So whatever likelihood value I get from there, I'll multiply it with P of x2 given mu comma sigma. Okay. We assume that the data points are conditionally independent of one another, and that's why we whatever probability we get for x1 and we get for x2, we multiply them for different values of mu and sigma. Now mu and sigma over here will take the same value, okay? So if I take mu over here, if I take mu over here as 1, I have to take mu over here as 1 as well, okay? And whatever likelihoods I get from applying the same formula, the function for the Gaussian distribution, I just multiply it, right? So that's how, in general, the maximum likelihood estimation works. Now I'll generalize this so that you can estimate it depending on any distribution that you have. You might have a binomial distribution or an exponential distribution or a Gaussian distribution. So I'll generalize this. So the main advantages of the MLE are that it is mathematically rigorous and less susceptible to individual values, as every data in the sample has equal weight in the calculation of the estimates of the parameters. So this method is very robust and can be used for any distribution. So over here in the example I just showed you with the Gaussian distribution, now I'll derive it for two distributions, the Gaussian distribution and the Bernoulli distribution. And yeah, so these are the general points that you follow when you want to estimate the population parameters from the sample that you have. Okay, so the first point is that you start with a belief. Start with a belief of about the population. Okay. So given a sample data set, I have to start with the belief about the population that the sample comes from. So in this example that I just showed you, I started with the belief that it comes from a Gaussian distribution. You can start with any belief that comes from a Gaussian or a Bernoulli or an exponential or a Poisson distribution, anything. The second part is that, you know, you derive the likelihood function that estimates the probability of observing the data using the belief in step one. Okay, derive the likelihood function that estimates the probability of observing the probability of observing the data using the belief in step one. Using the belief in step one. Just stick with me here, I'll explain what this is. So, derive the likelihood function that estimates the probability of observing the data using the belief in step one. My belief in step one was that it follows a Gaussian distribution. So derive the likelihood function. In this case, we already know what the likelihood function for the Gaussian distribution is. It's given by 1 by under root 2 sigma square pi exp minus half of x minus mu by sigma the whole square. This is my likelihood function that rests on the belief that estimates the probability of observing the data using the belief in step one. My belief in step one is that it comes from the Gaussian distribution, just for example, and this is the likelihood function. So I derive this function. Now for the Gaussian distribution, I know what the likelihood function is. But if you're conducting some research or you don't know what the distribution is, then you would have to derive the probability function, the likelihood function for the distribution that you assume. The third step is to take the natural logarithmic transformation. Okay, take the natural logarithmic transformation of the likelihood function. Now, why do I do this? It just makes calculation easy, okay? That's why I take the log of the likelihood function. So in the case where assume that the likelihood function is follows the Gaussian distribution. The samples follow the Gaussian distribution, and the likelihood function is this one, minus half x minus mu by sigma, the whole square. I would take the log of this, sorry, the natural log, which is ln, okay? And then I would go on to, it just helps me solve the equation faster because you'll know why, I'll explain why. And the fourth and the last step is that you estimate the parameters that maximize the log likelihood function. Estimate the parameters that maximize the log likelihood function. And how do you estimate that? Well, you take the derivative with respect to each of the population parameters that you're trying to estimate. Okay, and yeah, these are all the steps that you need to follow. For whenever you're trying to find the maximum likelihood estimation for any distribution, these are the 4 steps that you need to follow. And now I'll give you an example. I'll show you an example of how I'll derive the the formula for estimating the population parameter for both the Gaussian and the Bernoulli distribution. So just write these steps down and follow with me. All right, I'll change the screen. So just write those steps down and we'll go. So let's assume that I have a data set where the points are x1, x2, x3 all the way to xn, okay? And I have to find the parameters, the population parameters that will maximize the likelihood of finding these data points in my data set, okay? So the first step is that I start with a belief. I'm starting with the belief here that my dataset follows the Gaussian distribution. You can start with any belief. You can start with the belief that it follows a Bernoulli distribution or a Poisson distribution, whatever, Pareto, whatever. I'm going to start with the belief that it follows a Gaussian distribution. Okay. The second step is to write the likelihood function. Okay. So I'm going to write this data set as X. Okay. My data set follows the Gaussian distribution. So I'm going to write this as 1 by under root 2 pi sigma square exp of minus half to x minus mu by sigma the whole square. That's the maximum likelihood estimation. This is not a maximum likelihood estimation. This is a likelihood function for the Gaussian distribution. So I'm assuming that my data sets follow this distribution given some value of mu and sigma. Okay. So I can write this as x1 comma x2 all the way to xn given mu comma sigma is equal to, watch this, pi I equals 1 to n 1 by sigma under root 2 pi exp of minus half into x minus mu by sigma the whole square. So I assume that all of my points are conditionally independent of one another, right? So I have to, this is I over here. So I have to take the likelihood for each data point where this is the likelihood function. So I take x1 first, and then I take x2 first, and then I take x3 first. And whatever values of the likelihood I get from the likelihood function, I multiply them. Why? Because the data points are conditionally independent of one another. And what does it mean if the data points are conditionally independent? It means that if assume that A and B are two events, they are independent of one another, then this is equal to probability of A, okay? And probability of B given A is equal to probability of B. So if you want to find the probability of both these events occurring, you would have to multiply probability of A into probability of B, okay? That is what conditional independence means. And if you, and so that's exactly what I've done over here in this formula over here. Assuming that the data points are conditionally independent of one another, I'm just multiplying the likelihood that I get from the likelihood function, the probability that I get from the likelihood function. Okay. So the next step is to take the log of this. Now, why do I take the log? Is just to make the calculations a little easier, because we'll have to find the values of mu and sigma where this value, where the likelihood is maximized. If I don't take the log, I'll have to perform the chain rule on this. And performing the chain rule on this, multiplying it over and over again, where you have n data points, and this n can run for 1000 or 10,000. It's very cumbersome. So I take the log just to make the calculations a little easier. Okay, so I'll write this as natural logarithm of pi I equals 1 to n 1 by sigma under root 2 pi exp minus half xi minus mu by sigma the whole square. Okay, I've taken the natural logarithm of it. Now I'll simplify this a little further. Okay, so I'm not going to write this again over and over again. I'll just simplify this further. How can I write this? So now if you take the probabilities of logarithm, the first of the product becomes a sum. Okay, so I can write this as minus sigma I equals 1 to n. This negative point comes over here, and this will turn out to be 1 by, sorry, just trying to calculate it from here. It'll turn out to be 1 by 2 ln 2 pi plus half ln sigma square and xi minus mu the whole square upon 2 sigma square. Okay, I've just taken the log over here, and it's very easy to see how I did it. First off, the product becomes a sum because you take the log. Next, because you have 1 by under root 2 pi sigma square, it becomes half ln 2 pi, right? Because I can just take out square and I can bring the root out. And exp, ln of exp is nothing but 1. So I get this out as it is. This entire thing, it comes out as it is. So this is what I get if I take the if I take the logarithm of it. Now, to estimate where my parameters are maximized, right? Wherever I have the maximum likelihood, to estimate the parameters where I have the maximum likelihood of observing my data points that I have in the sample, I would have to differentiate it. I'll just call this LL, okay? LL is equal to this. So I'll have to differentiate LL with respect to Dow mu and Dow sigma, okay? I'll have to equate it to 0, right? To maximize it. So that's what I'll do next. So I'll take LL and I'll differentiate it with respect to U. So if you just solve it, I'll leave the solving to you as an example exercise or a homework. So if you just solve this, what you get is, when you differentiate with respect to mu, which is the mean, you get 1 by sigma square I equals 1 to n xi minus mu is equal to 0. Okay. So this can be reduced to mu equal to 1 by n sigma xi, where I equals 1 to n. Okay, that's it. So this is where our intuition meets mathematics. It says that to maximize the probability of observing all your data points in the sample data set, all you need to do is take the mean of your sample data set, and that is what will maximize the probability of observing your uh, data points in the population data set as well. Okay, this is where mathematics meets intuition, and we have proved that this is the case using mathematics. Okay, so that's what it says. It says that to maximize um, the population parameter mean, where you just have to take the mean of all the sample points, and that will be the population parameter mean. So similarly, if I take natural log of sigma, I get I basically get this as minus n by sigma plus 1 by sigma cube I equals 1 to n xi minus mu the whole square. So if I again equate this to 0 and I solve for sigma, which is the standard deviation, or take this as sigma squared, which is the variance, I get 1 by n is the number of data points, sigma I equals 1 to n xi minus mu the whole square. Okay, this is the formula for your variance. So this basically tells you that if you want to estimate your parameters, your population parameters from a set of sample data points, the best way to estimate those population parameters is to take the mean as the mean of the sample data points and the variance as the variance of the sample data points. If you're moving forward with the belief that your population data set follows the Gaussian distribution. That's what this says. Okay, and we have proved it mathematically that to maximize the likelihood of observing the data points in the population, the sample data points in the population, we just have to take the mean of all the sample data points and the variance of all the sample data points as the mean and the variance of the population data set as well. That's what we have done. See, that's the beauty of maximum likelihood estimation. It's brilliant. It's so intuitive and it's so easy to understand, and I really like it. So now let's do the same thing but for the Bernoulli distribution, just to give you a taste of the maximum likelihood estimation. And I'll run you through the mathematics again. So again, I start with the belief that my data set follows. I have a sample data set of, let's say, points. I have a sample data set of points, let's say, x1, x2, all the way to xn. And I assume that this sample follows the Bernoulli distribution. The population from which the sample comes, that population follows the Bernoulli distribution. I'm assuming, okay? So my belief is that the population from which the sample comes follows the Bernoulli distribution. That's number one. Okay, so if I know that that is the case, then I know my likelihood function for the Bernoulli distribution is given by f of x equals ncx. This is ncx, which is your c from combination p of x 1 minus p n minus x, right? This is the likelihood function for the Bernoulli distribution. Okay, and ncx is given by n factorial upon x factorial upon into n minus x factorial. Okay, that's what ncx means. Okay, so now I know that since this is my likelihood function, what I'm going to do is I'm going to do the same thing again. I'm going to take f of x1, x2 all the way to xn. And here, look, in the Gaussian distribution, I had to estimate mean and standard deviation or variance, right? Over here, what do I have to estimate? I have to estimate this value of p, and I have to estimate I just have to estimate p, right? Because N doesn't matter. I just have to estimate P. N can be anything. I mean, it's a population. You can take N as 100, 1000, 10,000, 100,000. But if you know that um, the sample follows the Bernoulli distribution, you just have to estimate P over here. X is the number of samples I have over here, right? So I know X and I don't care about N. So I only have to estimate P. So what I'm going to do is, again, to estimate it for each value of P, I'll have to take I equals 1 to N, NCX, XI, M, okay? Here I is the data point. I think we'll get confused in all the N, so I'll take this as M. The data points are M, okay? NCX, P of Xi into 1 minus P of N minus Xi. This is the same thing that I'm doing that I've done in the Gaussian distribution. Basically, since the data points are independent of one another, for each value of P that I find, I'll have to multiply the likelihoods, right? Now, again, I take the log of this, and I take the log of x1, x2, all the way to xm for some value of probability P. I basically get this, okay? I've taken the log over here. So if I take the log, what do I get? I get sigma I equals 1 to m ln of n factorial minus sigma I equals 1 to m ln of x factorial minus sigma I equals 1 to m ln of n minus x factorial. What I've done is I've just taken the log over here in this part plus sigma xi ln p I equals 1 to m plus sigma I equals 1 to m n minus xi ln of 1 minus p. Okay, that's all I've done. I've just taken the log in front of this and I've expanded in natural logarithm and I've expanded it. Okay, so I would urge you to try this on your own. If you don't get it, leave a comment, and I'll also provide the working for this in another video. But for now, I would urge you to just try it on your own, and you would see very easily how this comes if you take the natural logarithm of this equation. Okay, so now that I have to estimate for what value of p, which is the probability in my Bernoulli distribution, is the likelihood estimated for my population parameter, for my population, right? So I just differentiate this with respect to p. Okay, and if I do that, what I get is 1 by p. I'm just doing this over here in my head. So xi, all of this doesn't have any p in it. So when you differentiate with respect to p, this just cancels off to 0, right? It cancels out to 0, and you would get 1 by p sigma xi plus 1 by 1 minus p into I equals 1 to m n minus xi, right? That's what you would get. And now you have to equate this to 0. So once you do that, the value of p, once you equate it to 0 and you try to find the value of p, you would see that the value of p is given by sigma xi, where I equals 1 to m whole upon m into n. Okay, so m is the number of data points that we have in our sample. This is xi. N is the number of data points that we have in a population. This you will have to assume based on the problem that you're trying to solve. And this is just the sum of all the data points. So this is the value of p that you need to take for your population parameter, such that the likelihood of finding these points, of finding these sample data points in your population, is maximized. So that's it. That's what this is. That's what the maximum likelihood estimation is all about. And I hope you guys understood this. If you didn't, just watch the video once again. It's not very hard. And what you basically need to do is you just need to follow these 4 steps, 4 rules to tackle any problem that requires you to find the formula that maximizes the likelihood. Okay. So I'll stop the video here and I'll see you guys in the next video.